Hello, my name is Ben Fletcher and I'm one of the architects here at Codasip, and today I'm going to talk a little bit about SIMD and Vector and the differences and the similarities and the trade-offs, as there's always trade-offs in any engineering topic. So to start with, let's think a little bit about where you might use Vector or SIMD. So you might have an application where you have a relatively small embedded scalar processor. Maybe it's in a world where it's having to do some DSP and there might be some real-time constraints. If those real-time constraints are challenging, then it would be reasonable to put a small SIMD extension onto that processor to help meet those DSP time constraints. In a similar vein, you might, in a different market, have a scalar processor that has maybe a slightly larger SIMD or vector processor on the side, which is able to accelerate general purpose algorithms. So these might be the kind of algorithms where they're not obviously having a lot of parallelism in them, but the compilers are pretty clever and are able to use the ISAs to speed the execution up. And you could have maybe a more number crunching application where you have a comparatively large vector unit with a specifically small scalar on the side for times when you really are trying to do a lot of number crunching, and you want to spend that silicon area on the vector unit to get through that maths quickly, and you're really only using the scalar as a kind of a housekeeping processor. So there's three different options there. There's many more situations where you might use SIMD or vector, but I think the takeaway is that there isn't a one-size-fits-all solution to parallel processing and vector and SIMD. And what you need to do is think about your application, the workload you're going to be using, and try and find the right solution at the right cost point for you. Now, if we think about SIMD and vector and think about what they've got in common, they're trying to do quite similar things. So in a scalar processor, you have a register bank. Let's say in this processor our xlen is 64, and you might have an instruction come in and you want to process that instruction, so we're going to add two numbers together. You would take those numbers from the register bank, and the addition would be done and the output would be fed back and written back to the register bank. Now, what we're trying to do with both SIMD and vector is, with that one instruction, do more operations at once. So if we think about SIMD, SIMD typically uses a vector length specific ISA. So what we're saying there is that the registers that SIMD processes on, although they hold multiple elements, so for example we might split these 64-bit registers into 4 and then have 16-bit registers, or elements within that register rather, that we add together, and we do the same with the output to get the results. But the actual width of that register, that vector, is fixed. And that means that the SIMD instructions are very specific, and when you're writing your code, you end up with a binary that targets exactly that architecture. Now, there are some benefits to this approach. One of them being that if you align your existing register bank width with your vector width, this isn't invasive to add this into a low-end core. You can use the existing register banks to hold your vectors, and you can set up your computational pathways to do multiple operations in parallel, and it's relatively straightforward to add that capability. And if you can accept the lack of precision or the reduction in the size of the elements, so we're down at 16-bit addition here, if that's okay for your application, then it could be a good solution. If we look at vector, so vector is the vector extension for RISC-V is vector length agnostic. So if we consider a typical machine, it would have a whole separate register bank for vector, and we would have VLEN being the width of that register bank. Now, typically in the market at the moment, having a VLEN of 128 bits is pretty common. There's a lot of activity in that kind of space, but it's not limited to 128 bits wide. Much wider vector machines are possible. But the point here is that the ISA itself is agnostic to the vector length of the machine the code is running on. So if you could write some code to do your algorithm on a VLEN 128 machine, you could take that same code, you could run it on a machine with a wider vector length, and you would get some benefit from the perceived extra performance from that machine with the wider vector length. Now, how does that actually work in practice? Well, let's say that we are trying to do the parallel addition that we looked at for SIMD. So with vector, one of the first things you would do is a vset VLI instruction. And this instruction would give the machine some information about what you're trying to achieve, as opposed to saying exactly how we should do it. So we would give it some scalar registers, and we would give it some immediate values. So something like this might be typical. So here what we're saying is that the element size is 32-bit. So on our 128 bit wide vectors, we would get 4 elements in each register. And the M8 represents an L mol of 8. So what we're then saying is that we are grouping the vector registers together. So groups of 8 registers can be used in one instruction. So if we then had a vector add, and we were doing something like this, what we would be saying is that we're going to take the contents of register V8, 9, 10, 11, 12, 13, 14 and 15, and we'll add them to the group from V16 to V23, and we'd store them back in that original group of V8 to V15. So if we look at that, that's 8 registers times 4 elements per register, which gives us 32 elements that VAdd VV instruction will work on. Now, for vector machines, because you can obviously go very wide and you can group 8 registers together and you can have very small element sizes, one instruction can actually expand into many operations. And so there is actually no guarantee that all of these things will be done at once. But the idea is the architecture of the machine will make choices to work efficiently on the style of workload it's tuned to. So if we then consider how can you run this code on a wider machine, and why does this code not need to change? Well, I haven't given the full story on the code required to run this. There would be a loop, so your loop would go around like this, and you would be doing multiple VADs to get through your whole amount of data. If we increase to 256 bits wide, we're then looking at 8 elements. So we've got 8 registers that we're grouping together because of the M8. We've got 8 elements per vector, so now we can do 64 operations based on this single instruction. And the way this works is that we specify the total number of operations, the total number of elements we want to work on via the what I've called T1 here. So that's the number of elements left to work on. And in return, the vset VLI instruction passes us back how many elements will be operated on per instruction. So it basically tells us how many of those elements that we have left to work on are going to be covered by the next iteration of the loop. And then by keeping track of that and updating, in this case, the register T1 to make sure that we are counting how much work we've got left to go, that code becomes portable across machines with different VLAN. And although there's not, no 2 vector machines are entirely equal in terms of performance, you can then pick a a different vector architecture, and your code should run easily. So, two different approaches to parallelism, both useful for in different parts of the market. I think the story here is that no two vector machines are equal, and it's really important to understand the workloads that you're trying to process and the cost point of the solution to make a good choice in how to progress.